Okay, hello guys. So last lesson we talked about the differentiation principles, right? So today let's move into the next part about approximating change, okay? So here we said you want to find the differentiation. So first you can just try to calculate dy over dx, right? So it can equals to, so here it can be equals to dy over dx as limitation for h is very close to 0 and fx plus h minus fx, right? Okay. That means the two difference between fx plus h minus fx, right? And then we said, like here, like just using fx2 minus fx1 over x2 minus x1, right? Okay, so we can then say that here is for x plus h minus x, right? Okay, so then we can set here it equals to limitation for h approximately equals 0, and that is for fx plus h minus fx, and x plus h minus x is h, right? So only this value left. So also we can just consider this value as the changing y over changing x. And the left equation can be considered as a differentiation of the dy over dx, right? So now we're using a new symbol to represent for the differences between y and the x. Okay, so then we can say the delta y means the changing y over the delta x means the changing x equals to delta y over delta x. Okay, so then we can also say that delta y equals to the delta y delta x, or also can be considered as dy over dx. So then you can just write that as delta y equals to dy over dx times delta x. But then you can just consider like this is just approximately maybe for an estimation for some problems. So for example, like here, if the problem is that a circle of radius 10 centimeter, if the radius is increased by 0.1 centimeter, and approximately how much will the area change, right? So for this problem, we can set area equals to pi r squared, right? So also we set that dA over dr equals to the smaller change of delta A over delta R and equals to the maybe for changing A over changing R, right? So we're only using this part of it. So first, differentiation for A with R, that is for 2 pi radius. And the delta A over delta R can be considered as here, that is for the smaller change of area. Okay, so we have the small change of area. And then you said small change of R is for 0.1 centimeter, right? That is 0.1 centimeter. And you can set R here is 10 centimeters. So just put into it as changing area equals to 2 pi times radius is 10 centimeter. And then times the smaller change is 0.1 centimeter. Okay, that is for this problem. Hope you can understand it for of this. Okay. Okay, so here we already have the approximate change. Okay, so also we have like the solutions here, and maybe let's move into another problem like here. If y maybe here the volume equals to 2x cubed using the differentiation to find the probability percentage change in v. Okay. So maybe here we can set that dy or dv over dx can be considered as the changing y over changing x, or also delta y over delta x, right? It can be considered this true form. And we're only using this part of form. That is for the delta y, right? So it's that we want to find approximately percentage change in v. Okay, so first we can say that the change in volume is dv over dx. So here is for 3 times 2x squared, right? So power to put it above of it, and then power minus 1, right? And then times the maybe for here is change in delta x, right? So the problem is that when x changes by 2%, how much it will change, right? So here you can find that the final answer here you can set is for 6 times x squared and times the changing x. Okay, that is it. So for here, we already have this. So we said that it changes by 2%. We can say the delta x equals to 0.02x, right? So changing v equals to 0.12x cubed. Okay, that is it. And we already have the 2x cubed, right? So we can say that differentiation here is 0.12x cubed over 2x cubed. That is for 0.06 or 6%. So we can say that the v changes by 6%. Okay, that is for this problem. Okay, so That's it for today's our lesson. Hoping you can truly understand it for approximate change, but don't be worried. This is a very basic part, and just trying to solve some problems that you can understand it for all of this. Okay, so see you next time. Bye.